and he's going to talk about this regularization of Hamilton's principle for higher order Lagrangian systems.
Okay, thank you, Hernan. First of all, I would like to thank the organizers and the scientific committee for the opportunity to be here. And I also would like to congratulate Jair Koiller for his birthday, so congratulations. And, well, I will talk about this problem of regularization of Hamilton's principle. And first of all, a brief review of higher order tangent bundles. If you have a smooth, at least CK manifold, you have tangency of curves up to order k, and that's an equivalence relation whose quotient set we will know by this CK of Q. So we can actually, for our result, we will take Q to be an open subset of Rn's, since we will work locally, and our local coordinates will be written like this: Q0, Q1, up to Qk in square brackets, not in round brackets. We will indicate the actual derivatives of a curve with round brackets, and these square brackets are the I mean, you should think of those as analog to QV. Instead of QQ dot for TQ, we use these square brackets. So if you have a Lagrangian function on your k order tangent bundle of class Ck plus 1, at least we will need that, which is also regular, we assume that this Hessian matrix with respect to the last derivatives is a regular matrix. So you have your variational principle, which is to find a CK curve, you need derivatives up to order CK, defined on this interval 0h, which is a critical point of this action for 0h, with fixed values for the curve and its derivatives up to order k minus 1 at 0 and h. And you can think of this as a constraint problem in the space of curves Ck on Rn. So we know that we can write the Euler-Lagrange equations, but that is if you know that your solution is going to be C2k, then, and not just CK, then you can write this. Remember, when you work with TQ, you have to change delta Q dot by delta Q dot. So you are working with C2 curves instead of just C1 curves, which is enough in principle. I mean, for your variational principle, it will be enough in order 1 to work with C1 curves. But so if you know that your solution is C2k, you can write these Euler-Lagrange equations with these boundary conditions for the curve and its derivative up to order k minus 1. So you have some questions, some natural questions that you can pose. If you give any h very close to 0, I mean in the open set 0 up to some certain small h0 and close enough boundary conditions, do you have a CK curve that it is a solution to the variational principle? Or, I mean, do you have existence of solutions? Is it possible that your solution is automatically C2k? And if so, you can ask if that solution will be unique among the C2k curves. And also you can ask if it's unique in the larger space of CK curves. Okay? So you have results in ODE theory, for example, in this book that I mentioned here by Agarwal. You can, I mean, since this higher order Euler-Lagrange equations, using the regularity of L, you can write it as an explicit ODE of order 2k, at least locally. And you have results that will tell you that that kind of equations with close enough boundary conditions always have a solution, and it is unique among the C2k curves. However, as I say here, this does not settle the uniqueness in the CK setting. So what we will do is a proof of simultaneously we will get existence and uniqueness of solutions in the CK setting in a variational language instead of ODE theory language. So first of all, we notice that our Hamilton's principle is not regular at h equal to 0. What happens is that the constraint functions that sends your curve key to the constraint, to the boundary values for h equal to 0 goes into the diagonal of this product and cannot be a submersion. The problem is not that you cannot solve that for h equal to 0. You can solve the variational problem. Actually, in order to have a solution, let me go to the first slide, to this slide. If h is 0, this must be equal. Also, these given values must be equal. Also, this one. You have to extend your curve somehow to make sense of these derivatives, but however you do it, you will get the conditions. And your curve, it has to be just a point which sits on this point, on this Q0, and that's it. I mean, in that case, you have a unique solution. If you don't have equal boundary conditions, you don't have any solutions. So you just solve your problem, but that does not tell you anything about the solutions around h equals 0. Okay, you cannot infer anything for if you say, if I move the h slightly, if I move my initial conditions slightly, what will happen? What we will do is replace this problem, but an equivalent variational problem, which is regular at h equal to 0, and show that you have a unique solution for that. Our regularization procedure will be similar to the one that George Patrick gave for first order systems. And our motivation for solving this problem is actually we were thinking of discretizing higher order Lagrangian systems, but thinking of discretization, I mean, we want to define discrete Lagrangians not in several copies of Q, I mean in k plus 1 copies of Q, but rather in this Cartesian product of tk minus 1 of Q, tk minus 1 of Q. So we need to define an exact discrete Lagrangian, and in order to do that, we need uniqueness and existence of solutions for nearby boundary conditions and for small h. This h will be the time step for the discretization. So, first of all, we replace the curves on Q by curves on TKQ and introduce additional constraints. So we have these curves Q0, Q1. Each one of these will be in Rn, each one of these Qj. And so we get this new variational principle, which is finding a curve on TKQ. These curves, here we have these constraints. We say that each curve is the derivative of the previous one. And you have your action here and your boundary conditions, which these were the given values for the derivatives of your curve Q. So you just rewrote your variational principle, and now we will reparameterize each one of the curves Qj. Each one was living in a different derivative stage of the curve. So you define this uppercase Q of a variable u, which will go between 0 and 1 instead of 0 and h, because you have hu here. So this new curve Q0, Qk of u satisfies an equivalent problem, which is the following. You change your objective function. You have to divide by h, but because your parameterization forces you to do that, but this is a constant, so you get this new objective function, which looks exactly like the old one, but with uppercase Q. From 0 to 1, your derivatives become this because of the reparametrization, and you get this third equivalent variational principle, which is finding a curve on TQ. The differentiability degrees of each one of those will be, this one will be CK, and then it goes down up to this one, which is Z0. Z0, the last one. So you have to have, you're looking for a critical point of this, subject to, well, the derivatives became this, and the boundary values are exactly the same at 0 and 1, are given values for the curve. Now, the objective does not depend on h. The constraints do. They have an h here, but it is a smooth dependence. So, now we're going to integrate this. If you have, if the derivative of qj is this one, you just integrate to get qj is initial value plus h this. And you can iterate. For example, for k equal to, you have q1 is q10 plus h times the integral of q2. q0 you obtain by integrating q1, but you had q1 here, so you just plug it in, and you get an integral in terms of q2. There's a change of order of integration there that allows you to have only one integral in the end. There appears this factor there. And in general, you can write qj, all the lower order curves in terms of values at 0 of the different curves, and some integral with this polynomial factor here of the higher order curve, the higher order component qk. So in this formula, if you take u equal to 1, you have this uppercase q at 1 was the constraint dictated that it was this value q2. So here it is. So you get this was the initial value, this here was this initial value, and you change, well, u by 1 here, and you get this expression for the final values q2, for these final boundary values. And you can define these quantities zj as these integrals here. The idea of this is that if you know the q1 here, the q1s and the q2s, you can find zj. And if you know zj and q1, you can write q2. You can go from the endpoint data, q1 and q2, to q1 and z. Okay? And you use these quantities to write a new variational principle, which is the following. You have to find a critical point of this action where all you have to do is find the qk, because the lower order curves are defined by the formula that we had before, this integral here. So it's just a shorthand notation. This here is shorthand notation for this integral. And the constraints on qk are given by some quantities zj. The idea is these zj are the final boundary values in this case. Now these constraints are linear functionals of qk. Okay? You just integrate. This principle is already regular. You could solve it, but we will use an extra step in order to have nicer computations. And this extra step will be to change the basis of some space of polynomials. So you have this usual inner product of continuous functions on 0, 1. If you have a function and a vector value function, v, you use this shorthand notation, which is f times v is just the inner product of f with each component of v. We use this double angle bracket to indicate that it is a vector. This is not a symmetric bilinear operation. So the constraint that we just had, which were these, some integral equal to zj, are just this operation applied to some polynomial expression, which is this one here, applied to qk, which is a vector valued function. It's an Rn valued function. So it's just some a times, let's say, times qk. So this, let me go back. These polynomials here are a basis of the polynomials of degree at most k minus 1. When you have j equal to 0, you get k minus 1 there, and then the degree goes down up to 0. What you do is take another basis of this same space of polynomials, which are the orthonormal polynomials on the interval 0, 1. They are related by some constant invertible matrix, which relates some the original polynomials with the orthonormal ones. And we can rewrite the constraints. The original constraints were this expression here, z equal to aj qk. And, well, the a's were gamma b, so gamma goes outside. And you can write b comma q equal to something which will be the inverse of this matrix. You just move it there, and you get the inverse times z. So you replace the constraints hj qk equal to zj by bj qk equal to some other quantities wj. The z and w are related just by this change of matrix, this change of basis matrix, gamma k. So your new variational principle becomes finding, given h initial point and these w's, which are again the endpoint values in disguise. You have to find a continuous curve, which is a critical point of this action, where again the lower order curves are defined by some integrals here involving qk and the initial values. And your constraints are this inner product of b and the q's have to take some values w. Okay, now we are going to solve that problem. You have this objective function sh, the action, which maps the curve qk into this integral that we had before. You can think of this as defined on the curves c0, and also you can think of that as defined on ck. It's even better. You can still do the same, but we will work with both in parallel because we want results in both contexts. So there's the omega lemma, which says that if you have a map from a Banach space to another one, which is CR, then composition on the left in this case, but with that map is a CR map from continuous functions from some compact space to U to continuous functions to the same compact space to F. The compact space here M is our interval 0, 1. So you have a CR map, and composition by that map is a CR map between spaces of function. So our function SH is a composition of maps. You start from a curve QK, living here in Z0. You have this map I, which is completing with the lower order curves, which had these long integrals, these expressions, which you just compute using QK, and also the initial values. Then you compose with L. You get L of this, and finally you integrate. This I here and the integral are affine and bounded and are C infinity. the Lagrangian, our hypothesis before was that it was ck plus 1. So this composition here by the omega lemma is also ck plus 1. And so SH, which is this composition, is also ck plus 1. If now we regard SH as defined on the ck curves, we can append on the left here an inclusion ck included in C0. That inclusion is also infinity, it is linear and bounded. And also SH will be, by the same reason, a ck map defined on, a ck plus 1 map defined on this space of ck functions. And from now on, we will use this letter L to denote either 0 or k, interchangeable. We will work with, here, for example, Z0, and SH goes from Z0 to R, or from CK to R, we will just use the letter L. What we want to do is to solve the equation, which we could write like this. The gradient of SH, of our objective function, should be perpendicular to the constraint space. So first, let us compute this. We know that SH is ck plus 1 at a point qk, which is a curve of class CL, either 0 or k. So you take a deformation of that curve. We will try to compute this as a directional derivative. Since we know it's smooth, we can do that. So we can, if you had a deformation of the higher order component qk, you can find the lower order curves using the same formula as before. You just put an epsilon there. Nothing changed, just the epsilon. And you can get the variation of each one of these qj, which is just some expression using this part only. These are constant, so they don't depend on epsilon. And, well, you can do some computations to compute the directional derivative of the action in the direction of some deformation delta q. And it gives you the integral of something, which is in Rn dual for its u, times delta q. So this will be essentially our ds. So from ds we define the gradient of SH, which is just taking the sharp at each u. This is something in Rn star, so we just take the sharp operator with the Euclidean metric in Rn. Is it possible that, since the L was ck plus 1, so the partial derivatives are ck. Q is as good as this final component, so it is CL. So this expression here, which has a partial derivative of L and Q, is in CL. So you have a vector field in the space of CL functions. And again, using the omega lemma, one can prove that this is a CK map. I mean, SH was CK plus 1, the gradient is CK. That's as expected. So now we compute the tangent space to the constraint set. And first consider this inner product of vector valued functions on 0, 1, which is just this integral here. And the constraints in the last variational principle were exactly these ones. Bj comma qk equal to wj, and that we call that function we call gj. Okay. These constraints are bounded linear. It's just integrating, and they are C infinity. And the derivative are the same functions, gj, because they're just linear. So we define this, we collect them all in a function g, and the tangent space to the constraint set is the kernel of g. Kernel of g, actually it is this is parallel to the constraint set because they are linear. So it's just a translation to 0 if you want. And we call that kernel of G, this tangent space, we call E. The E orthogonal with respect to this inner product that we introduced in the last slide is the space of vector-valued polynomials of degree at most k minus 1. Okay, this Bj were these orthogonal polynomials. These coefficients are now vectors, and it is not difficult to show that the orthogonal of the kernel of the constraints is this space of this finite dimensional space of vector-valued polynomials. So we have a projection from E times E perp to E, which is given by this familiar-looking formula. You just take your vector delta qk. You just compute like this projection and use that for as a coefficient for Bj. So you have this sum here is an element of this type. So this is actually the E perp component of your vector delta qk, and you just subtract that. Now, what we want to find is where at which points the projection of gradient of H is 0. So we need to solve these equations. This equation here, projection of gradient at a point, at some certain point, which we split in an E part and an E perp component, should be equal to 0. And we want to solve this equation only for the QA component. I will say why in a moment. And also we want to solve this equation near this solution, which is the stationary curve, just QK equal to 0. So the curve actually does not move. The W values, which are the value of the constraints, also equal to 0. Some given values, some given initial values, and H equal to 0. I mean, if you plug this into the equation, you actually get a solution. So you know for sure that is a solution. And if you reconstruct that to a curve on Q, you get just a stationary curve, which stays at your given value for Q0. So in this equation here, we want that the partial derivative of this expression with respect to this variable here, which is what we want to solve for, should be a linear isomorphism. And these W's, these Q1s, actually the Q bars, I should say, the Q bars, the initial values for your boundary value problem, and H will be regarded as parameters that one can change, one can move in some neighborhood. And the point is that the QE perp component, the one here, will be completely determined by the W's. I mean, if you know the W's, you can, from using the constraints, you can know exactly what QE perp will be. So there's, you don't have to do anything with that component of your curve Q. So what we do is, just in order to compute the derivative of these expressions with respect to this variable here, we take a deformation of this stationary curve, this null curve here, of this form, epsilon times some vector delta q. And if you let me go to the expression here, gradient of h here. If you know that h is 0, which is where we are working, so this vanishes and you only get this here, delta partial L QK applied to this Q of u, which is this here. So you get this. So you have to project that term, just that term, and take variations at epsilon equal to 0. You just do some computations, and you get, when you apply the definition of P, you get some constant matrix here, which goes outside this bilinear operation. This is in curve G because E was curve G, and curve G was precisely, G was defined by Bj, comma something equals 0. So Bj times this, which is in curve G, is 0. So this sum here vanishes, and you only get this expression here. You have 0 here because Q at epsilon equal to 0, this was 0. And this is an isomorphism because this Hessian matrix here was regular by hypothesis. So that's your derivative, which is a linear isomorphism, and you can use the implicit function theorem. So you have a neighborhood of your parameters, which were the initial values, this W, which contained in disguise the final boundary values, and the H, containing the point where you were working, which was exactly this one, and a neighborhood of the constant curve, which was also the point that you were working with. In CL, in principle, this could be 0 or K. You have different, for each value of L, you have different neighborhoods here, but you just take the intersection. And you have a function mapping boundary conditions and H to curves, such that this psi, this CK function here, given the initial condition W's and H, is precisely the unique critical point in this neighborhood of the null curve of the last variational problem. So if you take L equal K, you obtain that this function implicitly defined here, this psi, has values in WK, okay, which is inside the CK curves. So you know that your curve will be CK. But by taking L equals 0, you also know that this will be unique in this neighborhood, which is in Z0. It's a neighborhood of the null curve in Z0, which is bigger than, and it's a larger space than this one here. So the curves provided by C are the unique solutions in this larger neighborhood in Z0. So you have existence in a small subset and uniqueness in a larger subset. The thing is that this curve here represents, in the end, eventually it is the derivative of your original curve is the derivative of order k. So your original curve will be C2k and will be unique in CK. So you have to actually add k to obtain the differentiability class of your original curve. So actually I will not speak about this. I think we're out of time, but one could reverse the regularization. That was what I was talking about now. And you have a solution. You can find then a solution of the original higher order Hamilton's principle with close enough, of course, close enough endpoint conditions Q1 and Q2. It will be automatically C2K, and it will be unique in a CK neighborhood of the constant curve. So the answer to our previous questions here is yes to all. I mean, you have existence of solutions in the CK context. It is automatically C2K. It is unique among the C2K curves, and it is unique in the space of CK curves. Okay, so now thank you for your attention.